Okay, great. All right. So, welcome everybody. It's good to be back doing these colloquiums again after the winter break a little bit. So today we're really lucky to have Nadir Jeevanjee join us. He's a physical scientist at NOAA Geophysical Fluid and Dynamics Laboratory based out in Princeton. Before he was there, he was a Henry Hess postdoctoral fellow at Princeton. And before that, he got his PhD in 2016 from UC Berkeley, where he worked with David Romps. And very recently, he was actually honored with the Henry G. I hope I say this right, Houghton Award from the American Meteorological Society um, for providing robust and comprehensive theoretical frameworks to illuminate complex phenomena in climate physics, which is really cool. And so congratulations on that. Today he's here to talk about some new insights into CO2 radiative forcing. And with that, excited to hear the talk.
All right, great. Thanks, Christian, for moderating, and to the host here for having me. So, indeed, the topic today is CO2 radiative forcing. Maybe before jumping in, I'll give you a little bit of a background into kind of my own journey and how I, got to studying questions like this, to give you kind of the context for this work. So, as Christian said, I got my PhD in physics from Berkeley back in 2016. I actually started academic life as a mathematical physicist, studying esoteric questions on quantum physics and general relativity. Even ended up writing a textbook on mathematical physics, and spent several years doing this, and didn't really turn to climate science until I was a TA for a course taught by Richard Muller called Physics for Future Presidents. And the idea here was to kind of teach the physics underlying, everyday technologies or technologies that were in the news, including the physics of renewable energy technologies, solar panels, and the electric grid and electric cars, as well as climate change. And so teaching this course really opened my eyes to the fact that underneath, all these front page problems was really the physics that I had been learning and knew and loved. So I got excited about applying basic physics to these problems, and ended up finding an advisor at Berkeley who worked on clouds and convection, and ended up doing a lot of simulations like the one pictured here, simulating tropical convection over the ocean. And so that's what I ended up getting my PhD in. As Christian said, I then came to do a postdoc in the Princeton Geoscience Department, and I had a fellowship that allowed me some freedom, and I'd always wondered about trying to understand the greenhouse effect better, both from carbon dioxide as well as from water vapor. That was something that always was kind of in the back of my mind as I studied clouds and convection, and this fellowship allowed me the opportunity to study it a little bit more deeply. And it was that fellowship that gave rise to the work which I'm going to talk about today, looking at CO2 forcing. Once the fellowship wrapped up, I then went to NOAA's Geophysical Fluid Dynamics Laboratory. It's kind of across the road from Princeton University, still in Princeton, New Jersey. And it's a major US climate modeling center that's also affiliated with Princeton. And it's probably worth knowing a little bit more about exactly what we do here. GFDL is a pretty remarkable place. We build climate models. In fact, the first climate models were built here. And I'll show you an animation of some of the latest and greatest of what we do. And what we do here is we simulate climate by simulating the weather. We build atmospheric models for the whole globe with all the dynamical equations and the thermodynamics, simulating all the weather and cloud physics that you see here. You get all kinds of storms in the extratropics and tropics. And then we couple the atmospheric model to a fully dynamical ocean model. Couple that to a model of the land biosphere, and try to model as much of the system as we can. And then depending on the application, we run it out for years, decades, or even centuries to try and predict and project climate change. And these predictions and projections feed into the consensus reports, which you might be familiar with, such as those by the Intergovernmental Panel on Climate Change, the IPCC. This is the most recent report pictured here. And just a few years ago, climate scientists were honored by the Nobel Prize in Physics for their work, and one of them was Suki Manabe, who was a pioneering scientist here at GFDL who developed our first atmospheric models, and along with oceanographer Kirk Bryan, coupled them to the ocean to create the world's first coupled models. So GFTL has a long history in climate modeling. At the same time, making the switch from physics to earth science into climate science was a little bit of a culture shock. And I know this audience has a lot of applied mathematicians and potentially people from, I don't know, maybe computer science and physics. So maybe some people have also, felt this little bit of a culture gap that in, some of sort of the more hard sciences or idealized sciences, you work with theories and quantities that are maybe a little more precise, a little bit more rooted in first principles. And one example that I often think of, and that'll be relevant for this talk, is the Planck distribution for thermal radiation. So this is this function pictured here, which probably most of you have seen. You can derive it from the first principles of quantum mechanics and statistical mechanics. And it tells you as a function of wavelength lambda and temperature T, what the density of emitted radiation is from a black body, thermal radiation emitted by essentially any object at a finite temperature. And coming from this background, this is the kind of object that I was used to working with. Turning to climate science, you're working with the messiness and the complexity of the real Earth, or perhaps comprehensive Earth system models, and you're working on a very practical problem, trying to predict or project the temperature decades into the future. And so often what you're looking at are plots like this, which is just a multi-model ensemble of temperature projections going out to 2050. And there's a lot of spread amongst the models. And this is often referred to as a spaghetti plot. You just get a lot of curves that are kind of crossing each other. And coming from a mathematical or applied math or physics background, sometimes one can lose sight of where the physics and math is. I even wrote an op-ed a little over a year ago, kind of putting forth this question. This is in the APS News, and telling a little bit of my, in more detail, my personal story about making this leap between fields. And so part of what I want to do here is, in addition to telling you about CO2 radiative forcing, is to bridge this culture gap by using these specific results as by using these results as a specific example. And so I hope that'll become clear as the talk goes on. All right, so that's a little bit of kind of my motivation and my approach. So the topic at hand, of course, is CO2 radiative forcing. That's, of course, a central character in the drama of climate change. So here's a plot that probably everyone has seen. This is just a time series of the CO2 concentration in the atmosphere from one observatory at Mauna Loa. This time series goes back to 1958, the International Geophysical Year. This is the oldest record of in situ CO2 observations, although in the intervening years, there's now, I don't know, 1 or 2 or maybe 3 dozen additional places across the Earth where CO2 is being monitored directly. And you see the CO2 climbing up steadily at a rate of roughly 2 parts per million per year, but accelerating, as you can see from the slight curvature in this curve. The red line are the exact measurements. There's an annual cycle there of the boreal forest breathing in and out with the seasons. That's an interesting topic, which we can talk about more. The black line is just the mean. So CO2 is going up. We can see that. We see that from observing stations all over the globe. We can also measure temperature. That's what's shown here on the right. 4 different data sets aggregating thermometer measurements from all over the globe and creating a global average. And they all agree really well. So it's unambiguous that CO2 is going up, the temperature is going up, and there's lots of evidence that says that the CO2 is in fact the cause. And that's also something we can talk about, although I imagine folks here are familiar with some of that evidence. So the CO2 forcing that's supposed to be causing this, what exactly is it? So let's make it precise. So focus here. I assume everyone can see my cursor. Let me know if not. In fact, maybe there's a way to turn this into a laser pointer. Yeah, there we go. So I hope folks can see that. So imagine a world with no greenhouse gases. Then sunlight comes in, the surface warms up, it's going to attain a certain temperature, and it's going to generate thermal radiation, which we refer to as long wave radiation, because its wavelength is longer than sunlight. And we call this, and it will go out to space. We call this thermal radiation going out to space outgoing long wave radiation, or OLR. And without any greenhouse gases, these 2 arrows would just balance. That's all that would happen. And this is kind of a homework problem that you can do in your second year thermodynamics course to figure out what the temperature would be given the amount of sunlight hitting the Earth. But now what if we have greenhouse gases? If you add greenhouse gases to this picture, like this CO2 molecule pictured here, well, the greenhouse gas is just a molecule that absorbs and emits in the infrared. So it's going to absorb this upwelling infrared from the surface, and it's only going to get re-emitted out to space from a higher altitude where the temperatures are lower. You know that temperature decreases with height, which you've experienced if you've ever climbed a mountain. And so the OLR now, if you just add these greenhouse gas molecules and you don't wait for the planet to equilibrate, but you just instantaneously add these molecules, all of a sudden the OLR now has a smaller value. And so the CO2 forcing is by definition just the difference in these OLR values when you add the greenhouse gas. And a few things about this definition. In this cartoon, I've gone from no CO2 molecules to some CO2 molecules, but you can define the forcing for any initial and final concentrations. Usually the initial concentration is taken to be the pre-industrial value of CO2, 280 parts per million. And often the final concentration is taken to be either the present day concentration or a doubling or quadrupling from pre-industrial. The other thing, as I mentioned before, is that this forcing is defined instantaneously before the system re-equilibrates. Obviously, to be in balance, this red arrow up here eventually has to equal the size of the yellow arrow. But for that, the surface has to warm up and make this bottom arrow even larger. The forcing is defined before that happens. It's just defined instantaneously as a reduction in OLR when you increase the CO2. And finally, what you see here, even from this cartoon, is that the only reason you get a forcing is that the temperature is different between the upper atmosphere and the bottom atmosphere. If the temperatures were the same, this arrow would be the same because the Planck function would be the same, and you wouldn't get a forcing. So this temperature contrast in the vertical is key to the CO2 greenhouse effect. And one of the things that we're going to do in this talk is make that quite precise. All right, so CO2 forcing is a central character. And as such, it's been studied for a long time. And the climate community has done a good job of calculating the CO2 forcing with some confidence in certain contexts. So for instance, you can go back over 40 years to this Charney report, which itself was a predecessor to the IPCC reports. And they evaluate the radiative forcing as being about 4 watts per meter squared per doubling for a doubling of CO2 from pre-industrial. You can also then turn to a recent assessment of climate sensitivity from just a handful of years ago, and they assess the forcing and get, well, the exact same value. There's of course been fluctuations of order kind of plus minus 10% in these assessments, but you see this value is really very consistent. And other papers looking at the details of CO2 radiative forcing, looking at single atmospheric columns and using the best radiative transfer models we have, so-called line-by-line calculations that compute CO2 radiative forcing with very, very fine spectral resolution, so resolution in frequency or wave number space. When they do these calculations and they look at the uncertainties, they find that it's very small, less than 1%. So in these ways, we're actually pretty confident about how we calculate CO2 forcing. But in other ways, questions still linger. So even though these benchmark models give very good answers that are pretty tightly constrained about CO2 forcing, if you run global climate models, like the kind we run here at GFDL and that I showed you in the animation, you actually get quite a bit of spread. So here's an assessment from 3 different model comparisons over the years. So the horizontal axis here are these 3 different model comparisons. The y-axis is radiative forcing. These benchmark models, the line-by-line models, are the triangles. And those, there's not too much spread. The circles are global climate models. And here you can see quite a bit more spread, plus minus, say, 15%, say. And so that's uncomfortably big for a quantity that's important as CO2 forcing. The other thing that happens, besides there being some uncertainty when we try and calculate CO2 forcing with full global climate models, is that there's also kind of lingering things we don't understand. So for instance, if you take a climate model and you just take a snapshot of the atmosphere on a given day at a given time, and then you quadruple the CO2 and ask what the forcing is, so the change in the OLR in watts per meter squared, you get a map of the forcing at every column. And that's what we did here for a GFDL model. And you see all kinds of structure. Forcing is strong in the tropics. It's weak or even negative at the poles. and there's all this structure over the land. And if you look in the literature, there's not really great answers about where the structure comes from and what variables it depends on. So that's a little bit unsettling, given that CO2 is such an important quantity. Another really important aspect of CO2 forcing is that it's logarithmic in the CO2 concentration. So you're actually supposed to get the same forcing for every doubling of CO2, not for every linear additive change in CO2. It's more that you get the same forcing per geometric change in CO2. And this has been known for decades. And yet, if you look in the textbooks, you get different explanations. And there was even a paper from just over 10 years ago kind of saying, well, why is this logarithmic? And positing, one of 2 or 3 explanations for this. And so what this is saying is that even though in some contexts we can calculate CO2 forcing pretty well, we could probably deepen our understanding of it. Because it's so important that we should be able to answer, all these questions about CO2 forcing. All right, so finally, we're going to return to the work that we actually did. And the idea here was to build an analytical model for CO2 forcing to try to get a handle on some of these questions. And to do that, you have to go back to basics and go back to the beginning. You have to go to the absorption spectrum. So that's what's plotted here. So this is the cross-sectional area per unit mass, kappa, plotted on a log axis as a function of wave number. Wave number is proportional to frequency. This is a particular band of frequencies in the infrared in which CO2 is radiatively active. And you see that there's the CO2 absorption spectrum spans orders of magnitude, and there's tons of fine-scale quantum mechanical structure. And one can spend a whole lecture describing all these features and where they come from, and it's quite fascinating. But for our purposes, we're just going to note that, if you squint, you can just kind of fit this with the straight line, more or less. And of course, this is a log axis, so these aren't actually lines, these are exponentials. So this is a piecewise exponential fit. So it's of this form, where I'm fitting kappa as a function of the wave number nu. And there's a few parameters in this fit. There's the wave number at the center of the CO2 band. There's a characteristic maximum absorption coefficient. Of course, it's not the exact maximum, but it's kind of a ballpark average value near the peak. And we refer to this kind of fit as exponential spectroscopy. And the last parameter is this parameter L, which tells you the slope of these lines, which is really telling you the rate at which the absorption coefficient decays exponentially as you move away from band center. And this parameter is going to turn out to be key for what follows. All right, so that's one ingredient, is making the absorption spectrum exponential. There's another ingredient we need called the unit optical depth approximation. So that takes a little explanation. So that's what I'm going to get into here. So I'm going to derive this approximation with cartoons. So imagine that you have an atmospheric column, and it's got greenhouse gas molecules in it. I've pictured here, water H2O molecules, so these little Mickey Mouse shape, but all of this argument applies to the linear CO2 molecule as well. And imagine that the concentration of absorbers is increasing exponentially downwards. So that's true for CO2 because pressure and density of just the regular air increase exponentially downwards. We all know that the air gets thinner as you go up. You know that from climbing mountains or flying in a plane. And since CO2 is well mixed, the density of the CO2 molecules just follows the density of regular air. It's a constant fraction of 280 or 400 parts per million. So this cartoon applies to CO2. And if you look at, say, if you chop the atmosphere up into layers and you look at the top 2 layers, the molecules are able to emit thermal radiation to space, but the density of molecules is pretty low. And so there's not that much radiation being emitted just because there's not that many emitters. Now, so we go down one more layer to this 3rd layer. Now, the density of molecules has gotten higher, and these molecules, they still have a view, they can still emit photons to space, just barely, but they still have a clear view of space, and so their photons are able to escape, and so you get a bit more emission from this level than you did from the levels above. Now, if you go down a little bit lower to these bottom two levels, the density of absorbers is higher, but their view of space is blocked by all the absorbers and emitters above them, and so you don't get that much emission to space from the levels below. So it seems like your emission maximizes at this kind of sweet spot in the middle. To formalize this, we introduce the notion of optical depth. And that's a function of both frequency and pressure. And for a given frequency, you can integrate the absorption coefficient at that frequency times the absorber mass from the top of the atmosphere down to whatever level you're at. And this integral is just the cross-sectional area of the absorbers times the mass of absorber in your column. And it's dimensionless. And if you think about it for a second, it's actually just telling you at this height, what is the total effective area of absorbers above you to the actual area of your geometric column. So this is this dimensionless number, and we actually see that it corresponds, that with this number, we can describe three regimes here. That these upper two levels have optical depth tau less than 1. The effective area of absorbers above is small and less than the area of the column. Down here, tau is greater than 1. The effective area of absorbers is greater than the area of your column. And this sweet spot where the emission to space maximized was around tau equals 1. And you can put equations all this and derive the maximum, and you get the same answer. I'm just giving you a heuristic derivation in pictures. And so what we're going to do from here on out is assume that all the emission stems from tau equals 1. Since the emission maximizes around here, we just kind of assume it's a delta function and that all the emission's coming from here. And that turns out to be a pretty good approximation. So if you do that, then you can take this integral in pressure that I just showed you, and you can evaluate it for CO2. The integral turns out to be pretty simple. You have the absorption coefficient out here. You have your CO2 concentration Q here. It turns out to be quadratic in pressure due to something called pressure broadening, which I won't talk about much more. You can ask about in the Q&A. But you get this simple expression for the CO2 optical depth. And if the emission comes from tau equals 1, well, I can just set tau equals to 1 and solve for the pressure. And that'll tell me the emission level at any frequency. So I just do that math. It's straightforward algebra. And this is what you get. And so now I can plot this, because these are all parameters that I know. And this is what I get. So now this is the emission level on the vertical axis as a function of the same wave number over the CO2 band that we were looking at before. And I've plotted the emission levels for two cases. A baseline case in the solid curve where CO2 has its pre-industrial concentration, 280 ppm. And the dashed curve is a quadrupling of that concentration. And what you see is that you get a sort of triangle here of emission levels, where emission comes from very high up in the atmosphere, actually in the stratosphere, when you're at the center of the CO2 band and absorption is strong. And this emission level declines as you go out to the wings and eventually just gets to the surface. And I'm going to describe this color coding in a second. And when you quadruple CO2, this emission triangle does two things. It gets higher and it gets wider. And it gets wider by an amount delta nu, and you can actually calculate what that is. You just quadruple the CO2 concentration and just ask how much wider the triangle gets. And you see the delta nu is equal to L, that's spectroscopic decay parameter, times the log of the change in concentrations. So you're already seeing this log scaling that the literature was kind of confused about not that long ago. And the log just comes simply from inverting this exponential. So this is already a hint that the log scaling is just coming from the exponential spectroscopy. So already this analysis seems to be telling us something. All right, the other thing that this picture allows us to do is to construct a heuristic picture for the CO2 forcing. Now, in the past, if you were running a radiation code that was going to numerically calculate the CO2 forcing, what you do is at every frequency, you calculate the difference in OLR at that frequency from these two different emission levels that have different temperatures. We're going to do something different. We're actually going to look at each height and look at the contribution to the OLR from that height and see if that can tell us anything. So starting up here, this green part of the curve that's actually emitting from the stratosphere, that emission is occurring at quadrupling, the dashed curve, but the solid curve doesn't reach up that high. So this is new emission from the stratosphere once I quadruple at 1x CO2, there was no emission from here. So this is actually new extra emission beyond what we had. So I'm getting more OLR. And that's a negative contribution to the forcing from the stratosphere because it's increasing the heat leaving from the planet. Don't worry, there'll be a positive contribution, which I'll describe in a second. From the parts of the curves color-coded orange, it turns out there's no contribution to the forcing. Because if I pick a point on the solid curve that's orange, say where my pointer is, then this there's emission from this level to space at the pre-industrial CO2 concentration. And when I quadruple CO2, I still get emission from this height. It's just coming from a slightly different frequency. But the Planck function varies so little across this tiny wave number interval that this is basically the same emission going from the solid to the dashed curve. So there's no change in the OLR when I go from here to here. So there's no contribution to the forcing. So where does the positive forcing come from? It comes from the surface. So these red parts of the curve are parts that were emitting from the surface at 1x CO2. But when I quadruple CO2, now they're emitting from a little bit, now these frequencies are emitting from a little bit higher. So you're not getting any surface emission in this part of the curve once I quadruple CO2. And so that's the part that gives you a positive forcing. And so if you buy this heuristic, then you can actually just basically write down an expression for the forcing. And that's as follows. If you quadruple CO2, you get a forcing which is proportional to twice delta nu, because there's two sides to the triangle, and the width that you get, or the widening, is just delta nu, which we know is L times log 4. And then you get a positive contribution to the forcing from this red part of the curve. And so you get that just by multiplying by the Planck function, evaluated at a characteristic frequency of the CO2 band times the surface and the surface temperature. And the negative contribution is just this same width over here, but now multiplying the Planck function evaluated at the temperature of the stratosphere at roughly 10 to 20 hectopascal here. And so that's a formula you can just read off from this diagram. You can also derive it analytically using the formulas that I've shown. And I'll give you a reference for that at the end. And so what this is already telling you is that the forcing from CO2 arises from a temperature contrast between the surface and the stratosphere. And in fact, a particular height in stratosphere, again, between 10 to 20 hectopascal, that's a height of about 30 kilometers. And so this is making precise the idea that I showed you in cartoon form before, that it's this vertical temperature gradient in the atmosphere that gives rise to CO2 forcing. All right. So now we've got the simple model, and we want to, let's test drive it. Let's see what it can do, both in terms of providing insight and also in terms of validating it. So the first thing to do is just to ask it, can we do a back of the envelope calculation? We know that from all this prior literature that the forcing is about 4 watt per meter squared. What does this formula give us? So I take this formula. I'm evaluating now for a doubling of CO2. So I've got a log 2 in here. And then I plug in typical values for the surface temperature of 288 Kelvin and a typical stratospheric temperature of 220 Kelvin. I plug in the value for the spectroscopic parameter that I get from fitting the absorption spectrum. And when I evaluate all this out, I get 3.7 watts per meter squared, right in the ballpark of this 4 watt per meter squared number that we saw before. There's some coincidences in here because this simple formula neglects things like water vapor and clouds. Those turn out to be relatively small effects that cancel. And so this is more or less getting the right answer for the right reason. It's definitely encapsulating the right first order physics. What about the spatial pattern of CO2 forcing? So we saw this before. This is just, again, a snapshot of the CO2 forcing calculated from a GCM. You see all this structure. And when I calculate this in the GCM, I have to take for each column, for each grid cell in this plot, I have to feed into the radiation code the entire vertical profile of temperature, of pressure, and of water. Well, in this case, of temperature and pressure. But what I can do is I can just take the surface temperature from this data set, as well as the stratospheric temperature at 30 kilometers, and I can feed it into this formula. What do I get when I do that? I get this, a map that looks strikingly similar. We were really surprised that the theory did this well. So all I'm doing here is evaluating this formula, not running a radiation code like I am in the left-hand panel. This calculation in the center is probably 10,000 times cheaper than what you see on the left. And yet the answer is remarkably similar. So that's a really nice validation of the theory. But we don't want to just validate the theory, we want to get insight from it. And the beautiful thing is that the nice thing about having a reduced order model is that it's got fewer degrees of freedom by definition. The only inputs are the surface temperature and the stratospheric temperature. So if we're seeing all this structure here, it has to come from one of those two variables. And it turns out that the stratospheric temperatures don't have that much horizontal structure as you move around in latitude and longitude. It's pretty smooth. And so that tells us that it must be the surface temperature, which is giving rise to all this structure. And in fact, if I just take the surface temperature data set from this snapshot and I plot it with the right color bar, it looks just like these other maps. And so what this is telling us is that the spatial variations in CO2 forcing, the fact that it's stronger in the tropics, weaker in the poles, there's some regions where it's highlighted, it even goes negative over Antarctica, it's just determined by the pattern of the surface temperature. And the negative forcing over Antarctica is just because that's one of the places where the surface can actually be colder than the stratosphere. And don't worry, that doesn't mean that Antarctica is going to cool with global warming. It's not. It's actually going to warm. And we can talk about why that is, despite the negative CO2 forcing. All right. So this formula helps explain the spatial pattern. And we also validated the formula against that. What about this intermodal spread? So we were talking here earlier how these circles represent the spread amongst GCMs. Each circle is one global climate model, and there's some spread in the CO2 forcing that they calculate. Well, again, this formula is telling you that there's only a few variables that influence the CO2 forcing. Now, unlike the last slide, surface temperature is not the likely culprit here because the climate models do a pretty good job of simulating present day and historical surface temperatures. You wouldn't really trust them if they didn't. And they do pretty well with that. But stratospheric temperatures actually don't probably get as much attention as they should. They're not that well constrained by what's happening at the surface because the stratosphere is kind of decoupled from the surface and from the layers of atmosphere below it. So maybe some of this spread here is from spread in stratospheric temperature. And so there was a paper led by Hao Jiehe, who's a colleague of mine, a postdoc, was at University of Miami, now at Princeton. He led a paper that appeared in Science just over a year ago. And there's a few different results in this paper, but one of the results was to take a number of different climate models. And so this is a scatter plot in which each model is a circle. And Hao Jie took a single radiation code, so not the radiation code that the GCMs were using, like here, but just a radiation code that he liked, that he could pass all the GCM data into, and to calculate the radiative forcing for a quadrupling. And you see that there's quite a bit of spread, plus minus 15% or something like that. And then he just took the air temperature at 10 hectopascal. That's this T strat here. And he just scatter plotted them. You see this amazing correlation with an R of 0.9. So that's an R squared of, over 80% of the variance is explained by differences in stratospheric temperatures amongst models, which if you look at the horizontal axis here, is a lot. There's a spread of over 10 Kelvin, over 10 Celsius in the stratospheric temperature amongst models. Now, this isn't the only thing causing spread amongst models. Also the fact, there's the fact that models are using their own radiation codes, which are, have to be approximate because they have to run fast. And so it turns out that about half the error that you see in this left-hand panel is from spread and stratospheric temperature, and the other half is from parameterization error. But the point here is that up until the advent of this analytical model, this was an entirely overlooked source of spread in GCMs. And the radiation community was thinking that the only thing they needed to do was reduce this parameterization error. But that's only half the story. And that's what this model told us. So coming back to these questions that we posed here, there are questions about spread in the models, understanding the spatial variations, and understanding this logarithmic scaling. And we see that, kind of miraculously, that the simplified model for CO2 forcing actually gives us insight into all of these things, which is quite remarkable for something so simple. And so I think that's a good example of the kind of work that can bridge the gap between a more mathematical or physical way of thinking and the kind of comprehensive modeling that has to be done to capture the behavior of the Earth system. All right, so to summarize, we leverage the exponential spectroscopy to build an analytical model of CO2 forcing, resulting in this simple analytical expression. And then this was able to explain a lot of things, like the spatial pattern of CO2 forcing, the logarithmic scaling, which just comes from the exponential spectroscopy, and the intermodal spread seen here. And before I close, I just want to point out that, as I said in the introduction, an overarching goal of my research, not just with CO2 forcing, but with other topics that I've worked on, is to try to bring a little bit of the spirit of physics into climate science. And so there's other, sort of avenues for work like this, which I want to alert you to. First of all, this work and other results like it are collected in a pedagogical article that appeared in the American Journal of Physics about 1.5 years ago, focused on climate sensitivity, CO2 forcing, the water vapor feedback. So if you found this interesting, I encourage you to look at this article, and it's aimed at physicists and mathematicians, and is pedagogical. I also co-authored with Tapio Schneider and Rob Sokolow a handful of years ago an article in Physics Today that kind of focuses more on the research frontier and outlines a number of important problems in climate science that can be attacked with the methods of physics and applied mathematics. Finally, I'm also on the executive committee of the APS Topical Group on the Physics of Climate. We organize sessions at conferences as well as a virtual seminar series, much like this one. There's one later this week from a variety of speakers within climate science and applied math and physics. So I encourage you to check that out as well. And so with that, I'll thank you for your attention, and I'm happy to take questions.
Great, that was a wonderful, wonderful, interesting talk, Nadir. I really appreciate that. So yeah, so I'll thank Nadir maybe first for a great talk, and then yeah, please, if you have questions, go ahead.
I can ask a question, if I may. Thank you for a very illuminating talk. Really, it helps to look at the details of what happens between here and the top of the atmosphere. Your model apparently took some phenomena apart and was able to look at each individual component, what comes from what. And my question is, you've done this for CO2. Is this possible to replicate this model or use this model like this for water vapor?
Yes, you can try something similar for water vapor. It turns out that the spectroscopy is also roughly exponential for reasons we actually don't fully understand, but that's just kind of an empirical fact. And so you can use that to build some understanding of, say, the water vapor feedback. So water vapor is a feedback, not a forcing.
Right.
We can talk about that. And so I and a number of others have done some work on that. And this pedagogical article that I pointed out has some discussion of that as well as further references.
Okay, thank you.
Yep.
Could I ask a question?
Please.
Hello? Could I ask a question, Christian?
Yeah, sorry. Yeah.
Okay, I raised my hand.
Oh, yeah.
Yeah, I second Hans in saying that you gave a really nice talk and you explained the concept well. I have two questions. The first one is just clarification. Now, the radiative forcing from doubling CO2, you mentioned that various people calculated 3.7. The latest AR6 says that the mean is 3.93 watts per meter square with a 12% scatter. And you had a slide earlier to say that there's no scatter if you use line by line. And so that's what I first thought. You mean that the errors are due to the parametrizations in the GCMs. That try to do the calculation fast. But then later you mentioned that that is not the case. Is that right? That wasn't what you were trying to say. The stratospheric temperature uncertainty seemed to have a bigger contribution. Now, the question is, if you specify the same stratospheric temperature in all this GCM, what would be the uncertainty? Instead of 12%, what is it?
That's a great question. I don't think we know the answer. I suppose you'd need to have a number of modeling centers run simulations where they nudge the stratospheric temperature to observations and then see what the spread across models looks like. So I don't know what the answer would be. I have glossed over other sources of uncertainty. I think I've told you the biggest ones, which are the stratospheric temperature and the radiation code error. But of course, clouds always play a bit of a role. And also the question of forcing does get more complicated than I've led on here. This whole talk was about the instantaneous forcing. So I hold the atmospheric state completely fixed, and I just change the CO2 concentration. But what happens in the real world, or even in a comprehensive model, is that if I quadruple the CO2 concentration, it'll take the surface a few years to start to warm up. It doesn't respond right away. But there's components of the atmosphere that respond to that change in CO2 concentration in days to weeks. So the stratosphere cools quite quickly in weeks, and clouds can respond. And if you account for that, those are so-called adjustments, the stratospheric adjustment and adjustments of clouds. They don't have to do with the surface warming. It's just the atmosphere feeling the effects of the radiative effects of the CO2. Those can differ amongst models. So KK, I think some of the spread that is quoted in the AR6 and in the Sherwood report probably also has to do with these adjustments, which I didn't talk about.
Yes, well, the CIMMYT models have a model intercomparison. Their radiative codes also have a radiative intercomparison. And as you mentioned, that some of the uncertainties are due to in the first few generations of the IPCC, they were using stratospheric adjusted the calculation while letting troposphere change. And the latest is called the effective radiative forcing, where they let troposphere change except those that involve surface temperature. And so some of these things can introduce uncertainties. I guess part of the problem, I was not sure, so I want to ask you, part of the problem is that, like you pointed out, the biggest components are stratospheric temperatures, but they cannot freely specify stratospheric temperature, right? They have to be model generated. And then these model generated different stratospheric temperatures, not necessarily due to radiative transfer, but due to their chemistry, the photochemistry, the transport, etc. And so that may account for the difference. It's not. So even if my question is, even if they use line by line in all these models, they will still be very large. And
yes,
so, yeah.
That's right. That's right. Because of exactly what you just said, that there's these adjustments from in the stratosphere and also in the troposphere, and the fact that the temperature in the stratosphere that's interactively predicted by the models, especially these days when you have interactive ozone and chemistry, including stratospheric chemistry, there's lots of processes that contribute to this spread, not just radiation. There's chemistry and other things. So that's right. Even if we applied line by line codes to climate models, you would still expect some of this spread to still be there.
Yeah, very good. I appreciated your talk that let me understand what the bigger issues are. Thank you.
Thanks for the question.
Yeah.
So I have
a few questions. One is less technical. So for the first question I have, so the first picture that you had, the simulation of this 3D sphere, where you had all these simulations all together, are these like something you generated from models, or is this something that?
You're talking about
Yes.
this animation, or
Yes, this one. If you
see if I can play it just to jog people's memory.
I mean, you could make it full screen maybe.
Second. Yeah, so you had a question about this animation?
Yes, that's correct. It's a beautiful animation, but there's one wonders is this from those large GCMs that you use coupled, or is this something that's just an animation basically?
No, this is model output. Doesn't seem to, oh, I need to play it here. This is model output. So this is a fluid dynamical simulation where you've chopped the grid up. This is actually a very high resolution simulation that probably only ran for a month or so. This is a very
Okay,
high
so
resolution
that was my next
model,
part. Yeah, yes.
which is why you can see such amazing detail of the cyclones. You know, you can even see the eye walls of the tropical tropical cyclones here. So yeah, the GCMs that we run are coarser than this, but it's basically the same thing. You are coding up the equations of fluid dynamics for the atmosphere and the ocean. You can't see the ocean simulation here, but it would be occurring. And then you couple that to the thermodynamics of cloud formation, of rain generation, of radiative transfer, and then you just press play, and it simulates, you know, global weather for as long as you ask it to.
Right, but to generate this picture, I'm pretty sure a few seconds. It's like demands like a lot of computation time and probably a lot of computational power.
Indeed. So certainly to run for, 100, 200 years, you have to go to lower resolution, but it's still very computationally intensive. And, we'll run on tens of thousands of cores at times for days or weeks to generate these simulations. So, I mean, we have a supercomputer located at Oak Ridge National Lab that, a large portion of it is dedicated to our work. Which is extremely computationally intensive. So yes, if you're looking at this and thinking, boy, that would be a really expensive model simulation, you're right. It was very expensive.
Okay, well, thank you. So for my next question is, I wanted to understand the logarithmic scaling that you did.
Yeah.
So then, so I was looking at your simplified expression for the radiative forcing, right?
Yeah.
And I wanted to understand, so how did you derive from the logarithmic scaling? How did you get the analytic model for the CO2 forcing with this kappa nu that you had? So I just wanted to see, like, how did you go from the alpha log to this kappa zero, this exponential that looks like a Gaussian? So yeah, so I was wondering
You're talking about up here?
Yes. So from this to if you go a few slides earlier.
Earlier?
Yeah, earlier. So yeah, so exactly. So you see this natural log here that you have there.
Yeah.
So there was a formula that you had before that kind of expressed that.
Yeah.
So can you say, like, how does this come into factor in this exponential that you kind of derive, like, mathematically? Or?
So is the question, how does I built the simple model. The question is, how does the logarithmic scaling arise from that simple model? Is that the question?
That's correct. Yes.
So we fit the absorption spectrum as an exponential, a piecewise exponential here, right? So is that part seem okay?
Yes, that's clear. Yes.
Yeah. Okay. Then I went through this idea that the emission comes from, at a given frequency, we can approximate all the emission is coming from the tau equals 1 level, where the optical depth equals 1, because that's this sweet spot where your emission wants to come from.
Right.
And so if you do that, if you combine those things, then you get this picture for the CO2 forcing. And the CO2 forcing is then just proportional to how much the width of the triangle changes when I increase the CO2.
Okay, so then this is the log scaling, right? From the exponential.
That's where the log scaling comes from, is that this delta nu
Gotcha. Okay.
is proportional to the log
Gotcha. Okay.
change in CO2 concentration. Yep.
Gotcha.
Good.
Yeah. I mean, it's a very nice talk. Thank you.
Good.
Any other questions? I just have sort of a general, well, maybe two general ones for since Emmanuel brought it up for the GCMs that you're using. This is just out of curiosity. For the initial condition, do you do any kind of 4D VAR to obtain an initial condition, or is it just a spin up, or do you know, just offhand?
Yeah, it's a good question. So it depends on whether at our lab we do both the initial condition problem, so that's a prediction problem, as well as the climate problem, which we refer to as a boundary value problem.
Mm-hmm.
So we have this whole suite of models, and sometimes we initialize them with data simulation. You'd have to talk to the data simulation folks, or whether it's 4D VAR or what flavor it is. And we use our models for prediction on timescales from days to decades, really, in prediction mode. And there's a whole kind of corner of the lab, or more than a corner, whole swath of the lab that does that. For our climate runs, we typically there we have a long spin-up run, a control run, with the couplet atmosphere and ocean, where we let the ocean slowly equilibrate and we get to a steady state. And then we run an experiment. We quadruple the CO2, or we start to increase it gradually. And then we look at what it does. So I think this snapshot was taken from a historical simulation, where you run the GCM with the time series of historical forcing agents. So the CO2 as it changed over time, the aerosols, the methane, everything goes in, and you watch the model slowly warm up. And this was like a random day in 1981 that we just happened to choose to do the radiation calculation for.
Okay, cool. Thank you. Yeah. And then the other one was just a general question. So that, this idea of stratospheric cooling is interesting to me, as the atmosphere, I guess, gets a little thicker. You have these emission bands.
Yeah.
Do you know much, or do you have any comment on the effect that this has on the jet stream overall, and some of these seemingly more common, I don't know, dips that we get? We get these blasts of cold weather, often referred to as a polar vortex.
Right.
Or how this plays into possible increases in sudden stratospheric warming events. I'm not sure. It's sort of an interest of mine, but I don't know.
Yeah,
too much
that's a good
about
question.
it.
So Christian is referring to there's some temperature gradients in the stratosphere, especially in the winter hemisphere, where the winter stratosphere gets very, very cold. Can be less than 200 Kelvin, right? So less than minus, can get to minus 80, minus 100 Celsius. And that temperature gradient actually then has a circulation associated with it, which is this polar vortex that you sometimes hear about. And if that temperature gradient breaks down somehow, if that polar part of the stratosphere warms up, then the temperature gradient breaks down, the polar vortex breaks down, and all of a sudden cold polar air can be free to travel down to lower latitudes. And that's sometimes when we have these very extreme cold snaps. I don't think that CO2 induced cooling would contribute for two reasons. One, it's a secular trend that's pretty slow. So yes, there is CO2 cooling. You can actually see it from satellites, especially in the upper stratosphere. It's one of these fingerprints of climate change that was actually predicted by Suki Minabe decades ago in a one-dimensional model. And he took sufficient care with the treatment of the CO2 radiation that the model showed stratospheric cooling, which was a surprise, but it turned out to be real. So I think the secular trend has been, maybe a handful of Kelvin over the satellite era, so over the last 40 years. So it's there, it's not huge, but also that's going to be fairly homogeneous in space, the stratospheric cooling. So I don't think it's going to give you impact the temperature gradients that are so important for sudden stratospheric warmings. That's my shoot from the hip answer. You could ask a stratospheric expert, but that's my take.
Okay, yeah, that makes sense, right? It would sort of be a global effect. Yeah.
I mean, one thing that's maybe I was thinking, I almost included a slide on this, so part of the reason that this paper appeared in Science is not just that it explained intermodal spread, but that if CO2 causes the stratosphere to cool, but then CO2 forcing is also a function of the stratospheric temperature, then as you add more CO2, the stratosphere cools. That increases the temperature contrast between the surface and the stratosphere, which then makes CO2 forcing stronger, according to the model that we've just been talking about. And so that's saying that CO2 forcing is not constant in time. As the climate system evolves, the CO2 forcing itself is state dependent and will change. And it turns out, and Hauja did a lot of work looking at this, calculating this in models, the CO2 forcing has actually increased in magnitude by about 10 to 15% over the historical period, just because the surface has gotten a little warmer and the stratosphere has gotten quite a bit colder. So that's a way in which the stratospheric cooling from CO2 actually does feed back onto the climate system.
That's interesting. Yeah, because there's been this sort of uptick in warming too, but this may also be related to reducing pollution levels of like SO2 in the atmosphere.
Oh, I mean, yeah, that's a whole other thing. And, you know, people have looked at whether it's reduced to the, related to the reduction in pollution. It seems like that's at best a fraction of what we saw. There's so much internal variability in the system, you know, from what happens in the tropical Pacific to the variations in the Atlantic overturning circulation, that there's potential other sources too. And I think what you see, this is a separate topic, but since you raised it, I think what you see, because we also had this hiatus, this warming hiatus, right? From, I guess that was what, maybe 2000 to 2010, something like that. And that's just the sort of the negative of the spike that we're seeing. So you have these kind of decadal scale ups and downs, and they're superimposed on top of global warming. And so when you have a negative phase, the warming seems muted. And you're like, oh, I've got a hiatus. And then in a positive phase, it's like, oh my gosh, it's jumped up. You know, what happened? But I think it's just the superposition of these signals. We don't understand the variability that well. But that's kind of what it looks like when you look at the recent past.
Okay, that's very interesting. Yeah. Thank you. Yeah. Okay. Any other questions for Nadir? Okay, if not, thank you very much. That was a wonderful talk and great discussion afterward. I really enjoyed that. And let's thank our speaker again. And we'll have a talk next week, I believe. And I guess we'll see you all then. So thank you.
Thank you.
Thank you. Appreciate the questions.